require entire and important. Shanghai maglev train designed to ferry passengers from the airport. Today, very fast trains. The University of Houston presents this series about the machines. Special relativity is one of the most remarkable discoveries in history, and in the next few minutes, I'm going to explain what it's about. Here's the setup. Consider this windowless train.
Check, check, check. Check, check. Check, check, check. Monitor, 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 monitor. Check, check. Check, check, check. Monitor, monitor. Check. Check, check, check. Check, 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 check. Check, 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 check. And the monitor, check. Better? Yeah? Good. Okay, good. Check, 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 check.
That's too low for me. I can, I guess. All right. In a bit. Fine. All right. Good morning, everyone. Welcome to Houston Oasis. My name is Abhishek Mathur. Can you all hear me? Think so? Okay. All right. Let's get started. We have a great Sunday for you today. Welcome to Houston Oasis. If you haven't been here before, welcome. And as you know, Houston Oasis is Houston's very own secular community. We are one of our key things is, please mute your phones, which I didn't follow because I was hearing myself here. Well, welcome to everyone online as well. We are a 501c3, and we're bound by some of our core values that you can see here. A couple of my favorite ones are human hands solve human problems, and meaning comes from making a difference. We have a great show for you today. And let's get started with some music from Mark Towns, and then we have a main talk by Andy Boyd, and then we'll have lunch later at Cat's Deli, and I'll let you know about that later. And then so let's get started with Mark Towns. Mark has played for us before many times through the years, and he's a groundbreaking jazz guitarist, and he's done flamenco as well, and salsa and other music genre. He's drawn inspiration from Latin jazz legends. His style fuses jazz and flamenco sophistication with the blues and rock influences of his Texas roots. Well, looking forward to it, Mark.
Thank you. Thank you.
Uh, Thank you, Mark. You'll be back. All right. Uh, uh, the main speaker today is no stranger to us, and he has spoken to us many times before, as well as he's a regular attendee at Oasis. But I do want to point out he's also a local celebrity in some ways. so. Uh, so he's worked as a professor before, and he was just telling me that he moved to a more company position after 10 years of teaching there. He received his AB with honors at Oberlin College with majors in mathematics and economics in 1981, and his PhD in analytics and operations from MIT in 1987. He spent 10 years as a university professor, as I said, and another 10 as chief scientist at PROS. He's received, again, okay. He's written various technical articles and journals, and of course, you might know him as one of the voices of engines of ingenuity as well for many years now. So please, Andy, take it away.
Gonna jump up. Letting it rip. So good morning. In a sentence, what is special relativity? It's recognition that the universe does some bizarre things with the way time passes. Actually, to flip this around, the universe simply does what it does, and the limited intellect provided by our 3.5-pound brains leads us to wrong conclusions about time. We assume there's a universal clock that keeps one time in the universe, that time passes identically for everyone, everywhere. 1 second is 1 second. But strangely as it sounds, when people are traveling relative to one, that's just not the case. And that is special relativity. When people are moving relative to one another, they see time passing at different rates. I'll show a video in a moment, but I'd like to start with a demonstration and a discussion of a few points. They'll be repeated in the video, but I think a little repetition doesn't hurt. So first, admissions. I lied when I said there would be no math. But I didn't want to scare anybody away. And the only one and only equation that I'm going to use today, we're all familiar with, and many of us used explicitly on our way over here today. When you look at the speedometer in your car, speedometer in your car, it tells you the speed at which you're traveling in miles per hour. In most of the world, it's kilometers per hour. But the key point is it's an equation. Speed equals distance divided by time. And that's the one equation we're going to use. But it's going to prove to be absolutely fundamental. And that's one of the reasons special relativity is explainable too. Okay, now let me I'm going to make a couple of obvious points because I really want to drill them in, but they're really obvious. If I get in my car and I travel at 60 miles an hour for 1 hour, I will travel 60 miles. If you get in your car and drive at 60 miles an hour for 1 hour, you will travel 60 miles. This frighteningly obvious point here is that if we travel at the same speed for the same length of time, we'll travel the same distance. And I hope that's just blatantly obvious. But that's actually going to become the key thing we're going to look at and say, oh, that's where special relativity comes in. Okay, so continuing with our observations. Travels with me on long distance cards too. So here's the point. I'm going to walk across here about 1 mile an hour. Okay. That might be a little bit faster than 1 mile an hour. So you see both Baxter and me moving at 1 mile an hour. Okay. But relative to me, Baxter's not moving. So that's going to be an interesting point that we're going to. In fact, I thought of an even better example. While I was flying, we look up in the sky and we see a plane going by at 500 miles an hour, and we say, wow, they're flying at 500 miles an hour. Meanwhile, I'm sitting on the plane and I look at my seat next to me, and she's not moving anywhere. So relative to me, she's not moving. Now, on the other hand, if she gets up to go to the restroom at the front of the plane, and she moves at 1 mile an hour, then relative to me in the plane, she's moving 1 mile an hour forward. Does anybody want to? So if somebody is on the ground looking up at my wife and wants to say, how fast is she moving relative to the ground, that would be 501 miles an hour, right? The 500 miles an hour from the plane, plus the 1 mile an hour that she's walking. unless she's walking at 3 miles an hour because she's in a hurry. That's pretty tough to do on a plane because you got to be elbowing people out of the way. So do we have any questions on what I've made at this point? Because it's supposed to be, we are truly in the land of the obvious, and I'm trying. Okay, but now I'm going to leave the world of the obvious and head into the world of what I consider exceptionally weird. So we'll have the same setup as on the plane with Sarah, but instead of Sarah walking to the restroom, I'm going to sit in the aisle, and I have a little gun that shoots little balls of light, photons. I'm going to shoot them toward shoot a photon toward the front of the plane. So I see it moving forward. Photons are pretty fast, about 1 billion feet per second. It's a big number to write down, so we usually just denote this by the letter C, and you probably see, or it's the same C as in E equals speed of light. So I'm in the plane, I shoot it forward, I see it moving forward at a speed C. So now someone down on the ground is watching this. I'm in the plane, going ahead at 500 miles an hour. And so from the ground, how fast do they see the photon of light moving? Plane's moving at 500 miles an hour, photon of light moves at speed C, shooting it forward. Any guesses? It should be 500 plus C, same as Sarah walking to the front of the plane. Interesting thing is, it's not. It's just C. Somehow the 500 miles per hour, it's lost. This is extremely weird. In fact, I want to emphasize again that this is really, really weird and completely counterintuitive. The people on the ground should see the photon moving at the speed C plus 500 miles per hour, but all they see is C. This fact was discovered as a result of an experiment performed by Albert Michelson and Edward Morley in 1887. It leads to a paradox that is seemingly unresolvable, and which I'll show in a moment. Well, this will be the video will show you how we resolve it. Physicists at the time couldn't find a way around the paradox. They were completely baffled. It didn't make any sense to them whatsoever. They stumbled around for 18 years, at which time Albert Einstein stepped in and said, well, here's an answer. And they all jaws dropped. And that made Einstein very famous. And I'm going to try to show to you here in a 4-minute video how this comes about. So away we go. I'll see you in 4 minutes. Special relativity is one of the most remarkable discoveries in history, and in the next few minutes, I'm going to explain what it's about. Here's the setup. Consider this windowless train car. We'll reorient it and remove the top so that we can see it contains a billiards table. The little eye next to the cue ball represents me. Now let's assume the car is moving to the right at 8 feet per second. To me, standing in the train car, the ball seems to be sitting perfectly still. Now let's add another element. Someone standing on a bridge looking down on top of the car. Relative to the ground, this outside observer sees the ball moving to the right at 8 feet per second, the speed of the car. Now suppose I strike the ball so that I see it moving toward the other end of the table at 10 feet per second as observed by me in the car. Our outside observer now sees the ball moving at 18 feet per second, 8 from the movement of the car and another 10 from the ball rolling. Nothing remotely surprising so far, but this is where things get seriously weird. Suppose that instead of using a billiard ball, we shoot a photon of light. From my location within the car, I see the photon move away from me at about 1 billion feet per second, a number we normally denote by the letter C. If I hypothetically run my train car at half that speed, we would expect the outside observer to see the photon moving at the combined speed of the car and the photon. But that's not the case. The outside observer also sees the light traveling at the speed c. What happened to the speed of the train car? This makes absolutely no sense, none whatsoever, but it's an experimental fact. To see how crazy this is, consider the following experiment. We shoot the photon from one side of the table to the other. Seen inside the car, it travels the width of the table. Seen outside the car, it travels the much longer distance shown here. but in each case, it travels at the same speed c. To put this starkly, if inside the car I see the photon moving at speed c, and outside the car you see the photon moving at speed c, we must see the photon move identical distances. But that's not the case. Is there a way to rationally explain this? The answer is yes, but it took a huge leap of imagination, and one that helped cement Albert Einstein's reputation. Let's take a look at the definition of speed. Miles per hour, feet per second. Speed equals distance over time. Let's write the speed equation for each observer. For the observer inside the train car, the distance traveled is 4 feet. We don't know the time, but we know from our speed equation that 4 divided by time must equal the speed c of the photon. For the observer outside the train car, we use the same speed equation, but the distance traveled is 8, and we're stuck. There's no value we can choose for time that will simultaneously solve each of these equations. And herein lies the amazing leap of imagination. What if we imagine time flows at different rates for the two observers? When 1 second goes by for the inside observer, 2 seconds go by for the outside observer. 3 for the inside observer, 6 for the outside observer. Mathematically, we express this as magenta time equals 2 times cyan time. And as a result, we can satisfy both equations. However, and this really bears repeating, this happens because time flows at different rates for the two observers. If the outside observer were to appear at a clock traveling with the inside observer, it would be moving at half the speed of the outside observer's clock. And it is pretty weird. I did want to kind of summarize again. So just to recap, this Michelson-Morley experiment with speed, with light just always seeming to travel at the speed c, is just weird, and it mucks everything up. And we couldn't figure out how to fix it, but the only way to fix it, as Einstein pointed out, was to let time pass differently for the group that's standing still. If the person standing still looks at the person going by, and he looks at a clock in there, would see the clock in that car going by moving at an actually physically slower speed. It's really exactly that. And again, it's not as if the moving people and the people standing still feel time going by differently. But their clocks, they would feel both normal, but their clocks would actually be ticking at different rates. So, and again, I think I got there. I don't know if you follow every detail, but the point is the only way you can get this thing to work with the speed of light always being the same is to muck around with time. And you can see why that was pretty exciting for physicists at the time. So some final points. This time dilation effect is only noticeable when the moving observer is traveling at a substantial fraction of the speed of light. So for us personally, it would take so much energy and so forth. We'll never run into it personally in our lives. We can't do it. But it's been experimentally verified. One way is to look at, because some things that do travel at the speed of light are subatomic particles. And what we find is that if they're standing still, they may have a decay rate of a certain length of time. But if we shoot them going really fast, it takes them much longer to decay because their time relative to ours is moving slower. And it fits right in with the experimental predictions. One of my favorite experiments, well, I think they use this for general relativity, but it works for special relativity too, is they took 2 atomic clocks and they made sure they were absolutely synchronized, very, very accurate. Then they bought one of the clocks a plane ticket around the world. I'm sure someone traveled with it. I've never seen that. But when they got back together, the clock that had gone around the world was actually moving a little bit, had moved a little bit more slowly than the clock that had stayed home. And it fit with experimental prediction. And just a couple other things. How much time slows down depends on how fast the moving observer is traveling relative to the stationary observer. So if, with the speeds we move, we don't notice anything. But if you get up there pretty close to the speed of light, the traveler is going at the speed of light, and time really, the closer you get to the speed of light, the more time slows down. and theoretically slows down to 0 if you can travel at exactly the speed of light. But no, that can't happen. And finally, I'll end with a paradox you may have heard of. People like, actually, I'll just say one thing before that. Once you start to follow the ramifications of this simple observation, it really causes your whole worldview to change. It permeates through all sorts of things in physics. I'm not going to do that because we don't have time, but like the idea of simultaneous events goes out the window. You can't say that two things happen simultaneously. Anyway, but the one really good example, and you may have bumped into it at some point, the twin paradox. Does anyone know the twin paradox? Okay. So this is a thought experiment, but this is exactly what the result would be that you take two twins and you send one twin off in a spaceship that's traveling close to the speed of light. And then that twin gets to wherever they're going and they turn around and they come back. If they were traveling close to the speed of light, the person that would have stayed home would have aged a lot, but the twin that had gone traveling might have only aged a year. So this is the twin paradox, is that this time dilation, if you could actually do this experiment, the two twins, when they got back together, would be very different ages. So that's kind of mind-blowing. In fact, if you remember the original Planet of the Apes film with Charlton Heston, that was based on this. He flew out near the speed of light. When he came back, the apes had taken over. Okay, with that, I hope that it gave you a more than a hand-wavy insight at relativity. So thank you. Susan. It's only called special because Einstein introduced something about 8 years later called general relativity, at which point, I think they were probably just calling it, I don't know what they call it, but they call it special because there's a more general relativity. And there the math is actually far more complicated, but it involves, I can say basically what it is. It involves gravity. And it seems that also that people that are in gravitational forces, like standing on the planet Earth versus in the middle of space, when you're in a gravitational well, your time goes more slowly than when you aren't under the effect of gravity. And the more gravity, the slower time goes. But that's just telling you what it is. I'm not going anywhere near the math of that one.
We're actually going to do a little coffee break. Then we'll do an extended Q&A with you, okay? Thank you. Coffee break, everybody.
I have a couple more things I want to point out. Next week, we have the blood bank. So please sign up online. You can go to the website and sign up there. There's a link there on the website. That's probably better. I should probably do that more. But we have the blood bank sign up online. And in 2 weeks, we have Seth Andrews coming on August 31st. So please be there and save your seat. It's probably going to be a packed room. And next week we have a great author coming in as well, Clint, and he's going to discuss a bunch of things. And please come in. And see you after the coffee break. Yep. What size is it? Queen. I'll let you know. Or you can ask around. Yeah. I'll let you know. Yeah. Sure. I'll let them know. I'll let them know. It's fine. Yeah. No big deal. All right, everyone, let's come back and we'll get started with one song from Mark here, and then we can go back to questions.
In the spirit of jazz, I have no idea what I'm going to play next. So. Thank you.
All right, before I call up Andy back up, I do want to make a few announcements. Firstly, the QR code for the blood drive is back here on your newsletter. You can scan that and set up your shift, your time to donate, and it'll be in a van downstairs on next week during the gathering. I believe, oh, I see it here. It says 9 a.m. to 1 p.m. For the donations. So it'll actually be early here, and we will be here, of course. And we have a Blues Night coming up on August 21st at the at the Big Easy, same as before. And you can let Will know if you're coming or anything. Yeah, we do have the Oasis Book Club, the Sum of Small Things, Wednesday, August 27th at Cafe Express. That'll be the book discussion, and you can talk to Ted about that, right? Oh, 7 p.m. Okay, got it. You can do the 4 p.m. to 8 p.m. if you like. It's just Cafe Express. All right. And also next Sunday will be BYOL, so that's something to remember. And Andy, you want to come back up? Oh, one more. Sorry, I have two more announcements actually. One is Susan is giving away a queen bed, and if you want to talk to her about it, you can do that. It's a sleep number. What was it? Yes, that. So our. Yes, we don't have a hat now. We have a basket to donate. That's cash donations and checks in there. And we also take, Zelle, Venmo, and we have a Simple Give recurring website as well. You can give on there. All the QR codes for those are here on there. You can set up the recurring donations on there so that it helps with our budget and plan better for better speakers and not Andy. Better than Andy, maybe. Or Andy's actually one of our highlights, actually. Let's be clear about that. But if you want to keep hearing more, all right. I'm not going to stop here. I guess we got time to kill, huh? That much? All right. So I do want to point out a couple more things as well. Let's make sure that actually, let's wait for that and come back.
Yes, Ted.
Yeah, obviously a fabulous talk. Really loved it. You mentioned there that some scientists in the 1800s had experimentally shown that from a moving object, if a light would not go faster than the speed of light.
Mm-hmm.
Is it easy? Roughly, do you have an idea how that experiment was conducted?
I do, actually, and it was kind of cool. But so the Earth revolves around the sun. So if you shoot a beam of light in the direction that the Earth is moving, then you should get the speed of you should. So the Earth's going this way and it's going around the sun. So if you shoot this way, you should get both the speed of light plus the speed of the Earth. And you can realize the difference because if you turn around and you shoot a beam back that way, then it should be going more slowly. And so that was the basis of their experiment. But they actually had a really wonderful device that they could twist in any direction and try it at anything. And no matter where they moved it, it was always the speed C. It's a very famous experiment, not just because of the result. It was a pretty well put together experiment too.
To add on that, the other conclusion that they saw. So if you like look at a star as you're moving towards it or away from it, you didn't see a change in the speed, but it was also evidence against the theory of an ether out there, that you had to travel through something.
No, oh, so should we cover general relativity now? Okay, thank you.
Sorry, Andy, I was a little shy before. So the universe works hard to make sure that the speed of light remains constant no matter what, right? Is that a fundamental thing that photons do when they interact with space-time, or is there an explanation for why the universe works so hard to keep the speed of light constant?
No, and in fact, I mean, it just is. At a certain point, things just are.
Right.
But what's interesting is it's so counterintuitive when you start to think about it. I mean, it just shouldn't work that way. And again, as I alluded to earlier, if we started to trace through all the weird things that this leads to, it just leads to a whole group of weird things. So it took physicists a while, even when they realized what a step of brilliance it was. It took them a lot of years to become comfortable with it, and many kind of rejected it for many years, but it's 100% accepted.
If nothing can travel faster than the speed of light, how can you get m equals, or mass equals mc squared? How do you get the c squared?
I don't recall. I do recall that the derivation was done in the same paper that that special relativity was introduced, and that the derivation itself isn't very hard. So I'd like to go back and look at it again, but I actually walked through it once and I thought, not very hard. So that E equals mc squared kind of pops out of this too. How deeply I want to get into it? I won't. I could get into it, but I'm past that now.
You know, perhaps part of that mystery too is how math can so elegantly explain these things, like, and it kind of like taken off of what Noe just said. I mean, c squared exactly is part of that equation. And the equation is so simple, E equals mc squared, almost like God is a mathematician or something, you know? I mean,
Yes.
Sorry, just another
Sure.
comment. And I've seen the derivation where that c squared comes from, but I'm sorry, I just can't do it off the top of my head. But one of the things that's important to note is that things only move at the velocity c if they're massless. Anything with mass has to go slower than the speed of light. And that's a consequence of the Higgs field.
So, hi there. I know you mentioned about what this might impact, and you said you weren't going to go into it, but are there at least some general topics that we could look up to see where this has been studied, applied, what it impacts?
Chat GPT.
Oh, okay.
Global positioning. And exactly how? I do remember. I'm trying to remember the connection. Come on, Eric, you're doing good. Oh,
You have to take relativity into account in order to get the right to correct for it, so that you get the right positional information for the global positioning satellites. So your phone actually has to receive information that's been modified according to general relativity.
yeah, thank you. Again, I think I was talking over the break. One of the really interesting things about this was physicists were always working very much in the real world prior to this, particles, waves. But when Einstein said time doesn't work the way we think it does, it really kind of opened the door for physicists to start thinking very wildly about what our universe is like. It kind of gave them free rein. And so a lot of the stuff that we've seen that's come out, if you read it even in the popular literature, it's kind of beyond comprehension, or beyond your imagination. Susan?
Did you just make that video for us today, or did you make it years ago? Or
Oh, no, I did finish it just in the last 3 months. That's about 3 months of work.
Oh,
And I will probably post it. But this is probably the biggest audience it will get. There's a lot of stuff out there. I mean, there's a lot of stuff out there that you're competing with. So, but I will say it's fun. I have my Adobe software and I make all the pictures and stuff like that. Fun.
Have there been any major modifications to the theory of the general or relativity?
None that I know of. Now Eric's going to come back and talk about a different space.
So what you haven't gone into is what is gravity, and that's very much an open question. But in terms of modifications, there are theories that say that the speed of light actually is variable with distance, space. There are some that have modified gravity theories, things to explain where dark energy is coming from. Are they right? Time will tell. I think they aren't.
Yeah, I think a lot of that stuff is not well accepted. That's pretty cool too when you come up with a theory like that and it holds up so well. But then again, this is worth mentioning that it's in the context of Newton before Einstein. So Newton came up with all these laws of physics, Newtonian mechanics we call it now, and they held up brilliantly for a long time. But when Einstein came through, he said, these are modifications we have to make. So.
Oh, and a tie-in to modified speed of light. That's one of the things that the religious apologists come up with to try and say why the universe is really only 6,000 years old and not as big as you think it is.
Can you explain how or if quantum mechanics derive the theory of relativity?
Okay, it doesn't. They're really kind of two separate things. And in fact, Einstein himself was never really very comfortable with quantum mechanics and spent a good part of his latter career trying to show why it wasn't perfectly correct. But they're really kind of separate things. They are separate things. When they do quantum mechanics, they have to take into account relativistic effects in the theories. I like the question, though.
Yeah, I'm very, very much a humanities person, so my mind is like blown. But I do like science fiction a lot. And so is it true that when people go out to space, they do age less quickly than us here?
Yes.
Okay.
Only a little tiny bit at any of the at any of things we're doing. But yeah, a little tiny bit, yeah. In fact, did I once calculate a guy that I worked with that flew 250,000 miles a year? I think I figured out how much slower his clock had moved over the years. Point 0.0000. Yes.
If time slows down near massive objects, does that mean the universe itself is aging at different rates depending on where you are?
You have to be careful. Observed time is passing at, if I'm in one location, wherever that may be, and if I could see clocks at different places that had different gravitational strength, then in fact, yes, I would see that the clocks at those different places were moving more slowly than seeing, which is pretty wild. So anyway, this is fun because I didn't know what everybody had in terms of their experience with relativity. A lot of it shows up in science fiction these days. So so I don't. Perfect. Again, thank you very much, and I hope that it helped you out.
Thank you, Andy. And I think he'll be after the talk here as well if you want to continue any of the conversations. And we also have lunch at Katz's Deli. It would be better if you guys can carpool to there. There's better parking here than there, apparently. So something to keep in mind. I do want to point out a couple more things. Maybe I'm a little more organized, better than the Gaddafi talk I did earlier. One item is I do want to thank all our volunteers, the audio team in the back here. You can see they've set up a great, cool setup now. And you can learn all about it if you want to volunteer with us. And then I do want to thank the coffee team, all the setup people helping us today. Thank you for everyone for coming as well. I do want to I have one more thing as well. On the Houston Oasis website, we have a banner that says Giving Tuesday fundraiser. It actually goes to our T-shirt website. We have new T-shirts. If you want to go there and order it, and it'll come straight to you directly. I think there's like a campaign thing going on it, so it's like a delayed shipping, but you'll get the shipping within a couple weeks. We have a couple new designs in there, and we have the existing designs on there as well. All right, let's do one last song from Mark Downs.
Thank you.
Yep. Go ahead, Susan. Fair enough. All right. Thank you, everyone. And this was a great Sunday. Thank you, Mark. Thank you, Andy, for the great questions. And I'm looking forward to warp speed. That's all. That's all I care about. In all this, all the equations are learned only for that. All right. Thank you, and we'll see you at Cat's Deli or next week. Let me know if you have any questions. Thank you.